Hello and welcome to the second video on 3D printing for repair. In this video we will take you through the analysis phase. After this video you will know how to identify the most important characteristics of your part to be able to make a 3D printable version of it. You will also be able to decide if your part is feasible for 3D printing. The analysis phase is the first phase of the 3D printing for repair process. This phase is the backbone of the whole process. It will give you more insight into the product and the part. This will help you to make the right decisions in the redesign and manufacturing phases. Before the analysis phase, we need to find out which part is broken or causing the problem. Usually, disassembling the product is necessary to get to the broken parts. If you need to disassemble the product, make sure it is unplugged first. Here we have two examples of products with broken parts. The photo on the left shows a broken switch of a water cooker. The photo on the right shows a keyboard with a loose key. An important thing to consider is part completeness, since it will influence your analysis process. If your part is complete, it will be easier to find all the shapes and measurements you need. However, if your part is incomplete or missing, it will be more difficult to remake. But not impossible. You will just need to pay more attention to the rest of the product to find out how the original part looked like. Now you have found your broken part and we can go into the analysis phase. We will look at three main topics: product architecture, part configuration, and part feasibility. The product architecture is about how the part relates to the product. What is the function of the part and how does it fit into the product? The part configuration is about the part itself. What shapes does your part have and what part characteristics are important? The part feasibility is about whether you can 3D print your part. After you're done analyzing, you will be able to see if you can recreate your part with 3D printing. Now let's move on to the product architecture. In this section we will take a look at the product function, part reference points, essential elements, and tolerance and fit. Let's start with the part function. It is important to know what the exact function of your part is. This will help you to find the most important part elements and characteristics. Try to be as specific as possible when defining your part function. You can state your part function using a verb-noun pair. Verbs can be, for example, move, protect, hold in place, facilitate. And nouns can be other parts. For example, the switch pushes the on-off button of the kettle. Nouns can also be users or input and ingredients. For example, the printer tray facilitates paper insertion, or the blender whisk mixes the batter. Next, we find how the part fits within the product. If your part fits very tightly into place, you will have narrower tolerances to work with during the redesign. There are three main categories: moving parts, normal fit, and push-press fit. The image shows the gap size that you should keep between two parts for each fit type. Also, press fits can even have a negative gap size, which means that the green part is larger than the whole of the striped part. Note that this gap size is a rule of thumb and that it will also depend on the accuracy of your printer. Getting gaps smaller than 0.5 mm will be tricky on most printers. To ensure the right fit, it is good to do some testing before printing your final part. You might also need to do some post-processing, such as sanding, to make your part fit. We will now take a look at the part reference points. Here you want to find how the part relates to other parts in the product. This goes beyond just screws and snap fits. The image shows a number of ways in which parts can match or relate. This can be through connections and physical interfaces, but also through similar shapes. This will help to make your part fit with overall geometry, assembly and function. Now you know more about how the part fits within the product. The following step is to take a closer look at the part itself. In this section, we will take a look at general dimensions, geometry and complexity, part features, manufacturing and material, part requirements and forces, and finally, the essential elements. You can think of general dimensions as a box in which your part fits. It is a lot easier to work with a part that fits in the printer. If your part is larger than your print area, you will have to split up your part. After printing, you can then glue the sections together. However, this will make your part weaker. Looking at the general dimensions can also help you to determine the shapes of the part. For example, the ring shown in the image looks circular, but it is actually oval. Seeing this in the analysis phase will help you measure the part when redesigning. Understanding the geometry and complexity of the part will help you see how the part is structured and to plan on how to reproduce it. The image shows both shape and complexity types. These will influence how difficult it will be to measure and reproduce your parts. For example, measuring a complex curve or freeform shape will be difficult and time-consuming. The same goes for part with a lot of additional bodies and/or features. During the product architecture analysis, we looked at part reference points. However, there are more features that are important for a part to function. Think, for example, of drainage holes. These are not related to any other part, but are very important to make sure the part functions. Identifying all the features in your part and seeing what their function is will help you to identify the essential elements of your part later on. Finding the original manufacturing method and material of your part will help to understand some part requirements. For example, a part made out of a high-performance plastic will require more strength, or a rubber part will require more flexibility. Also, finding the original manufacturing method will help to find how a part will change when you 3D print it. We will spend some time comparing injection molding to 3D printing in our next video. Plastic parts typically have an indicator stamp that identifies the type of plastic they are made of. The parts will have a number of requirements, depending on its place and function in the product. For example, parts next to a heating element will need thermal resistance, and housing parts most likely need impact resistance in case the product falls. Identifying these requirements will help you make better decisions for the redesign, manufacturing and testing of your part. For mechanical performance, it is a good idea to also map out the forces it needs to resist. This will help you to find part sections that will need to be reinforced or that need other modifications. Now it is time to select those characteristics that are essential for part functioning. This will help you to decide what part characteristics you should keep in your part redesign, or which one you could simplify or eliminate. Make a summary of those part elements that are important for the part to fit and function correctly. The part reference points and other part features are a good place to start. The picture shows an example of a part that was simplified. The curvature at the back was not considered as an essential element, but the pivoting points were. Finally, it is time to ask yourself the big question: can we 3D print this part? For this, we will provide you with a checklist that you can use to make the decision. Additionally, we will provide examples of a feasible and a not feasible part. It is difficult to define exactly when you can 3D print a part or not, due to the large variety of parts, part requirements, and printing methods and materials. For some 3D printing methods or materials, it might be easier to achieve certain requirements than for others. However, here are our recommendations for FDM, since it is one of the most common and available technologies. We found that it was difficult or practically impossible to print parts that need to be food safe, that need to withstand large forces or high temperatures, that require very tight or accurate fit, that have very small and fine detailing, smaller than 0.5 millimeters, that require very smooth or low friction surfaces to function, or that have complex curvatures or complex or inaccessible cavities, as these are difficult to measure and clean during post-processing. If your part does not fall into these categories, then you can very likely print it. To give an example, let's go back to the broken parts at the beginning of this presentation. So we had a broken switch of a water kettle and a loose key of a keyboard. The switch of the water kettle was a success. It took a few iterations and design changes to get it to fit and function properly, but it is repaired now and still holds up. The keyboard, on the other hand, was not a success. The original part was a metal hook with measurements smaller than 0.5 millimeters. This made the redesign very challenging. After 35 hours of work, there was still no favorable result. Therefore, you should choose your battles. Not all parts are feasible for 3D printing, and some are, but take too much time and effort. In summary, the analysis phase consists of the product architecture and part configuration. The product architecture describes how the part fits in the product. The part configuration describes the part shape and part requirements. The analysis phase is important because it will not only tell you if it is feasible to print your part, but also point out the necessary information for you to redesign and manufacture a 3D printable version of your component. Now, let's move on to the redesign phase in our next video.